Hey, welcome back. In this chemistry lesson, we'll be introducing what molecules are. Molecules are compounds, but they are held together by a different type of bond rather than ionic compounds. In this case, it is the covalent bond as opposed to the ionic bond. So, let's get into this. Just quick, as sort of an introduction or whatever, think of elements, substances, that we find in their pure form, not bonded with any other elements. So, do we experience any of these in our day-to-day lives in nature? Well, pretty much no. The noble gases do tend to stay as monoatomic, just by themselves. Xenon can form compounds. Now, none of the noble gases are really all that common on Earth. Argon does make up 1.5 to 2% of the atmosphere. But the only real other substances that are common that we run into that are purely elemental are the oxygen and the nitrogen and the hydrogen in the atmospheres, with hydrogen being really, really nowhere close to as common as oxygen and nitrogen are. But that's about it. So everything around us comes in the form of compounds, and tons of the ones especially that make up living things are molecules, not ionic compounds. So the bond that holds together atoms of molecules is the covalent bond. And the covalent bond is a bond where valence electrons are shared between atoms. So if you have a diatomic molecule made of two atoms, the electron is not permanently transferred from one to the other, like we saw in ionic compounds like sodium chloride. The sodium atom loses its electron, and chlorine takes that electron and keeps it. It adds it to one of its orbitals. Molecules, the electrons that are not paired, those freely available valence electrons, orbit back and forth between orbitals of two or more atoms bonded together. So a molecule, the word molecule can mean different things. One definition is all molecular compounds are neutral as well, same number of total protons and electrons between all the atoms. Compound that is held together with covalent bonds. But molecules can be pure substances as well. And we can also use the term molecular bond and covalent bond interchangeably. Now, examples of molecules, diatomic molecules made of just two atoms. So O2, N2, H2, fluorine, chlorine, bromine, iodine, and astatine will also form diatomic molecules. They'll bond to themselves. So it's a pure substance. It's not really a compound. It's a pure molecule. But then there's carbon monoxide, hydrochloric acid, HCl, bromine monofluoride, so the element bromine, and a single fluoride, known as the monofluoride, to tell you how many there are. Bromine monochloride, chlorine monofluoride, you get the idea. And the noble gases are classified as monoatomic molecules because the smallest unit of a pure substance, that can mean a molecule too. So a gold, like a sample of pure gold, is made of, we could technically say, gold molecules of gold. For the record, that is the case, but also for the record in this class, when I say molecule, I'm only talking about really compounds held together by held together by covalent bonds. But sometimes, O2, I'll call that a molecule as well. So the chemical formula for a molecular compound, that just tells you how many of each atom you have. So CO2 is carbon dioxide, H2O is water, methane, I forget what some of these other ones are. So butane, butane is C4H10, glucose C6H12O6, and then oxygen and ozone. Those are not in their simplest ratios. Why don't we just say O? Why don't we say CH5, divide everything by 2, or C2H5? We can't do that because if you remove or if you reduce the number of atoms, you no longer have the same molecule. So for example, if we divide C6H12O6 in half, that gives us C3H6O3. Well, that's not glucose, it's glyceraldehyde. And if we divide that, glyceraldehyde is not CH2O. That's what formaldehyde is. So back in chapter 7, we talked about formula units. With ionic compounds, you can do this. You can reduce them down because they are just repeating units. But molecules are standalone compounds. Glucose molecules can link together to form what's called a polymer, but that's no longer glucose. Then it becomes something like starch or glycogen, perhaps. It turns into a completely different substance. I'll show you some models here after a bit. And besides just the chemical formula of a molecule, the actual shape they take is important. Now, in ionic compounds, they tend to form crystals out of repeating patterns. Molecules don't really do that because they're much more simple, they're microscopic, and they don't really link together. But still, the shape that a molecule has determines a huge amount of its function. So we use molecular structure, there are ways of drawing it, but we also use physical models to show you what the molecule looks like. The other tricky thing with this is two different molecules can have the exact same chemical formula. So the only way to distinguish them from each other is to see a 3D model or to draw it out. There are ways to draw them and ways to build them. But in any case, they're called isomers. So for example, here is glucose, glyceraldehyde, and formaldehyde. They all are made of the same ratio of atoms, a 1:2:1 ratio, but they're completely different molecules. Glucose is sugar, tastes good. Formaldehyde, don't taste formaldehyde. Don't ever do that, please. I don't really know what glyceraldehyde does, so I wouldn't eat that either, though. Here are a bunch of isomers. So butane and isobutane have the same chemical formula, but the atoms are arranged in a unique way. Here we have dimethyl ether and ethanol. Again, same chemical formula, C2H6O, but arranged in a different way. The only difference between glucose and galactose is this group, the H and the OH here, those are flipped. So if we go back to this picture, that would be this spot right here. If we imagine that the oxygen and the hydrogen are up top, just like they are here, and the hydrogen on bottom, that's a really simple basic change. It didn't change the chemical formula, but it is a completely different molecule with different properties. Galactose, in that case. There's also a principle called chirality. So there's a molecule called thalidomide that was used for, I think it was for morning sickness, and it was given to pregnant women in the 40s and 50s, I believe. A molecule, so we think of it like your hands. My right and my left hand are mirror images of each other. Now, if I look at my hands like this, if we looked at a silhouette of my hand, you wouldn't be able to tell which one's the right hand, which one is the left hand. So that's sort of a conceptual problem we have. We draw these molecules as two-dimensional, but in reality they are three-dimensional. The right and the left hand are different. These fingers bend this way, these fingers bend that way. Although a 2D silhouette of the hand, it would look like there's either two right hands or two left hands as I put them up there. But it doesn't work that way. Now, these chiral molecules can be hard to distinguish, so many women were accidentally given the drug with the opposite, the mirror image of thalidomide, and it caused, as you can see, a huge number of birth defects, and it wasn't caught. The reason for this wasn't figured out until many years later. So this is why we need to fund science and have an intelligent public health policy and framework for catching things like this. Moving on. So as I said, we can't use formula units because when you reduce the number, when you write the formula, that's basically the same as just taking atoms off of your molecular model, and that completely changes what it is. There's also no such thing as a molecule of sodium chloride, which is an ionic compound. Again, they form repeating units and patterns. Molecules don't do that. And another difference, so we're comparing molecules and ionic compounds. Another difference is most molecules have really low melting points. Galactose melts at 167 degrees Celsius, glucose, fructose, different sugars. Pretty low temperatures. That's just, for fructose, that's just a little higher than the boiling point of water. Whereas ionic compounds, the vast majority of them melt at temperatures above around 400 degrees Celsius, but many of them, a huge number of them, still have melting points way over 1,000 degrees Celsius. And a lot of that is due to the nature of the ionic bond, is a much stronger bond. So melting is basically forcing the atoms to no longer be bonded to each other. Covalent bonds are much weaker because of the sharing of electrons, whereas ionic bonds are much stronger because of the electrostatic attraction. Another difference is that a lot of molecular compounds that are gases at room temperature, we don't really say they have a melting point because they'll do something called sublimate. They'll go from a solid directly to a gas. And these happen at crazy low temperatures. Carbon dioxide sublimates at a temperature close to negative 80 Celsius. Dry ice is carbon dioxide, so if you've ever seen dry ice before, you can go on YouTube and look up videos of people messing with it. It looks like snow, packed together snow, but you cannot get it to melt. It just simply evaporates. Ozone, even colder. Carbon monoxide, even colder still. And oxygen, crazy negative 218 degrees Celsius. You can make liquid oxygen, but you have to put it under really extreme conditions, and then it boils as fast as it can. That actually wraps this up. So we're just introducing molecules and the covalent bond. Next time, we will be discussing specifically how covalent bonds work, it looks like. So I'll see you next time.